225 miles of ground move in under 2 minutes. 9 meters of lateral offset appear in a single motion. 3 aqueducts cross that same line on the map. All 3 are built to fail exactly where they cross it. 24 million people live within reach of the shaking. Not one of them chose to. Not for a volcano, not for a comet, or a storm, or anything that arrives from outside. This is not a story about weather. This is the San Andreas Fault. The story is about its southern section, the stretch running from the Salton Sea toward the mountains above Los Angeles. It last broke open in the year 1680. Every year since, it has stayed locked. Cities do not build themselves around a hazard on purpose. They build first. The hazard turns out to have been there the whole time. Palm Springs sits a few miles from the trace. Indio and Coachella sit almost on top of it. San Bernardino grew directly across a fault capable, by conservative estimate, of a magnitude 7.9 earthquake. Interstate 10 crosses the line. So does Interstate 15. So does the Colorado River Aqueduct, which carries water more than 200 miles from the river to the coast. None of this existed when the fault last ruptured. In 1680, the land here was empty desert and scrub, home to Cahuilla communities who left no engineered structure across the break. Today, the same ground carries interstate freight, drinking water for a metropolis, and roughly 2 million people living within a few miles of the trace. Tens of millions more sit inside the wider shaking radius. The fault did not move to meet the city. The city moved to meet the fault, one subdivision at a time, without asking what was underneath. 2 separate lines of evidence, built decades apart by different scientists using entirely different tools, arrive at the same number. One line of evidence comes from space. Global Positioning System stations, bolted into bedrock across Southern California, track the ground's motion to within a few millimeters a year. They confirm the Pacific Plate grinds northwest against the North American Plate at roughly 2 inches annually, a rate as steady as a clock. The other line of evidence comes from mud. Marsh sediment at a handful of sites along the fault preserves a record of past ruptures, layer by layer. Each layer is datable by the carbon locked inside decayed plant matter. The satellites measure how fast strain is accumulating right now. The mud measures how often that strain has actually been released across the last 2,000 years. Neither method was built to check the other. They agree anyway. The fault has been storing motion since 1680 at a rate the satellites can time to the month. Translated into feet of eventual slip, the total comes out close to 20 feet either way. Long before instruments existed to record any of this, people living along the fault noticed the ground behaving strangely. Oral traditions carried across generations in these inland valleys describe sudden violent movement of the earth. They describe water behaving unnaturally. They name specific places for what the ground had done there. These accounts were not treated as data by the scientists who arrived later. They were filed away as folklore and mostly forgotten. Paleoseismology has since confirmed the ground really did move this violently and repeatedly on roughly the timescale the oral histories imply. The instruments did not discover the danger. They caught up to something already described in a different language using a different kind of evidence. Here is a fact that is simple to check and hard to explain away. In 2014, a study conducted for the University of California looked at Los Angeles buildings built before modern seismic codes. It identified roughly 1,500 older concrete buildings. Engineers call these structures non-ductile concrete, a technical way of saying they crack instead of bend. The city separately identified more than 13,000 wood frame buildings with a similar weakness. Known as a soft story, it typically means an open ground floor built for parking. The city passed a retrofit ordinance covering both categories the following year. As of the most recent public reporting, only a small fraction of the concrete buildings had completed full construction on their retrofits. Owners have until 2041 to finish the work. That deadline assumes the ground will wait. The fault does not read ordinances. It does not know which buildings have permits pending and which have permits closed. The list exists. The ground beneath the list is still moving at 2 inches a year, regardless of paperwork. Every locked fault on this planet runs the same arithmetic. The San Andreas is not even the most overdue example. In Turkey, the North Anatolian Fault has ruptured in a documented westward sequence for most of a century. Beginning with a magnitude 7.8 earthquake near Erzincan in 1939, one segment after another has broken in order, marching steadily toward Istanbul. The most recent major link in that chain, a magnitude 7.4 earthquake, struck the city of Izmit in 1999. It killed more than 17,000 people and stopped roughly 60 miles short of Istanbul's outskirts. Seismologists studying the sequence describe the fault as moving segment by segment. The pattern is one they can already trace on a map, toward the one major city the chain has not yet reached. In New Zealand, the Alpine Fault runs the length of the South Island. Its average recurrence interval is roughly 300 years. Its last rupture was in 1717. Government scientists there now estimate the probability of a major rupture within the next 50 years. Depending on the model, the odds run somewhere between 1 in 3 and 3 in 4. Alpine fault earthquakes behave less like random chance and more like an overdue appointment. Set that number beside the southern San Andreas, silent since 1680, and the two faults look like siblings separated by an ocean. Same debt, same clock. The comparison holds until you add one detail neither Istanbul nor the South Island can match. Nowhere near the Alpine Fault do 24 million people live inside the expected shaking radius. Nowhere near the North Anatolian Fault does a single rupture threaten to sever 3 water aqueducts feeding the same metropolitan region at once. The physics is identical. The exposure is not. Why has this particular section stayed quiet for 346 years when its neighbors to the north have already spoken twice? Why does a fault this well mapped, this well measured, still get treated as a rumor rather than a scheduled event? Who decided a retrofit ordinance could stretch across 25 years for buildings that may not have 25 years left before the ground under them moves? What exactly are 40 million Californians waiting for, given that the deficit is not a theory, but a measured, published, peer-reviewed number? And if the cycle is this well understood, why does preparedness still lag so far behind the certainty of the science? Ask most people to name a California earthquake, and they will reach for the same one: San Francisco, 1906. It is the fault's most famous relative, the one that made it into textbooks and disaster films alike. A geologist named Andrew Lawson had named the San Andreas Fault 11 years earlier, in 1895. He mapped it after a smaller feature near a lake south of the city. When the ground broke in April 1906, Lawson chaired the commission that traced the rupture. It proved his modest local fault actually ran the length of the state. The resulting report, published in 1908 and still called the Lawson Report today, became the founding document of American seismology. It also cemented 1906 as the reference point for every San Andreas story that followed. That reputation is not undeserved. The 1906 rupture killed roughly 3,000 people and burned much of San Francisco to the ground. But the comparison flatters the northern section at the southern section's expense. The northern segment broke in 1906, 120 years ago. The southern segment has been locked for 3.5 centuries, considerably longer, sitting beneath a population many times larger. Yet it rarely appears in the same sentence as its famous northern sibling. The fault most people picture when they hear the big one already had its big one. The one still waiting has stayed almost anonymous. By the end of this, it will be clear why a young geologist spent more than a decade hand-digging trenches across one desert creek. He was counting earthquakes nobody had seen. It will be clear why the United States Geological Survey assembled 300 scientists to build a scenario it deliberately never called a prediction. And it will be clear exactly what happens, minute by minute,
in the 90 seconds after this fault finally lets go. The mechanism underneath all of this fits in one sentence, though proving it took a century. Two tectonic plates are sliding past each other along a boundary running the length of California. Friction is the only thing keeping them from doing it smoothly. Where the rock is locked, strain builds instead of releasing.
Where the rock is free to creep, it slips a little every year and never stores enough energy for a large earthquake at all. The San Andreas is not one fault behaving one way, it is three sections behaving three different ways. Some creep quietly, some stay locked and loaded like a drawn bow. Picture a garage door on a rusted track. Most of the door inches upward smoothly, tooth by tooth. One section catches and holds while the motor keeps pulling. Nothing gives until suddenly all of it does at once. The door that seemed motionless jumps the distance it should have moved gradually. That caught section is the southern San Andreas. The motor still pulling is a tectonic plate that does not get tired and does not stop. In the late 1970s, a young geologist named Kerry C. chose an unremarkable stretch of marsh north of Los Angeles. He wanted to test an idea nobody had proven. The site was called Pallet Creek.
If a fault ruptures through soft, wet ground, the layers on either side of the break slide against each other. Each rupture leaves a distinct diagonal scar, sealed beneath whatever mud settles on top of it afterward. Count the scars. Date the mud above and below each one using radiocarbon methods. In principle, you can read the fault's entire history the way a tree's rings record its age. In practice, it meant years of manual excavation, careful photography of trench walls, and patient dating of fragments no bigger than a fingernail. C kept at it through the late 1970s and into the 1980s. By the time he was done, he had identified 9 or 10 major ruptures reaching back to roughly the 6th century. The intervals between them ranged from under 50 years to nearly 3 centuries. His stubborn problem was never really about digging. It was about proving a fault's memory could be read from mud at all, when nobody in seismology had managed it before him.
There was nothing cinematic about the work itself. No glow, no smoke, no dramatic instrument reading to point a camera at. Just a shovel, a trowel, a paintbrush for clearing dust off buried soil, and small radiocarbon samples mailed off one trench wall at a time. Here is the twist most people never expect from that decade of fieldwork. C's data did not reveal a fault ticking along on a tidy schedule. It revealed the opposite. The intervals between ancient ruptures varied by a factor of 6. The tidy idea of an earthquake arriving like clockwork, once every 135 years on the nose, turned out to be an average. Underneath that average, it was masking enormous scatter. What looked from a distance like a steady rhythm was closer to a loaded pattern. Not random, not regular either. The ground had been keeping score the entire time. It simply was not keeping score the way anyone expected. Under normal conditions, solid rock behaves exactly the way its name suggests. Rigid, dependable, unchanging within a human lifetime. Along a locked fault, that appearance is a kind of disguise. The rock is not static. It is bending, storing elastic strain the way a metal ruler stores energy when flexed before it snaps back. From the surface, nothing looks different. Underneath, the crust on either side is wound tighter every year for as long as the friction holds. When the friction finally fails, the stored bend releases all at once, not gradually. That is the same appearance versus reality trick this fault has been running for 346 years. It is worth remembering later because the ground keeps performing it at every scale, from a single creek bed to an entire section of coastline. Thomas Jordan directed the Southern California Earthquake Center from 2002 to 2017. He coordinated hundreds of scientists across dozens of institutions studying exactly this behavior. His work helped popularize the term now attached to that stored strain: slip deficit. It describes the gap between how far the plates have actually moved and how far a locked fault has allowed the surface to move. The plates do not pause simply because a section is locked. They continue advancing at the same steady rate regardless. Every year that passes without a rupture adds another increment to a deficit that has nowhere else to go. It is not an abstract number sitting in a research paper. It describes, in advance, how far one piece of California will eventually lurch relative to another in whatever single motion finally closes the gap. Here is the mechanism, stated as plainly as the physics allows. Elastic strain accumulates for centuries along a locked section of fault. It does not leak away gradually through small, harmless tremors.
Small tremors release only a sliver of a percent of the stored energy. The fault waits until the friction holding the two sides together finally exceeds its limit. Then, the entire accumulated deficit releases in a single rupture, lasting somewhere between 40 seconds and 2 minutes. The ground does not slowly drift into a new position. It jumps there. A creek bed that has flowed straight for 3 centuries can be found the morning after, offset by 30 feet. The water is still running, just now running sideways around a bend that did not exist the day before. The earthquake is not really the danger by itself. The stored decades are the danger. The earthquake is only the moment they get spent. The Carrizo Plain, the same stretch of desert where Wallace Creek sits, offers the clearest illustration of this on Earth. Airborne laser mapping conducted across the plain in the 2000s let researchers measure its surface with unmatched precision. The scans reveal streams and ridgelines offset sideways again and again in the same direction by amounts that stack neatly across dozens of past ruptures. The land does not improvise a new pattern with each earthquake. It repeats the same kind of motion in the same direction on a schedule the rock itself has already recorded. Reading it does not require guesswork. It requires patience, a shovel, or, increasingly, a laser scanner flown in a low-altitude aircraft. If stories like this hold your attention, subscribing helps more of them find you. There are other locked faults on this planet keeping the same kind of ledger. The southern San Andreas is not a one-time anomaly dressed up as a pattern. Smaller sections of the broader fault system show the same rhythm on a scale short enough to observe directly. Near the town of Parkfield in Central California, a different stretch of the San Andreas behaves with startling consistency.
It produces a magnitude 6 earthquake roughly every 2 decades. It struck in 1857, 1881, 1901, 1922, 1934, and 1966. The interval looked regular enough that scientists in the 1980s formally predicted the next Parkfield earthquake. They said it would arrive by 1993, an unusually bold, testable forecast for a field that almost never makes one. The predicted earthquake did not arrive in 1993. It arrived in 2004, 11 years late by the average. A fault system had just spent decades proving how badly a superficially tidy pattern can still betray the people who trust it too literally. The lesson is not that the rhythm is fake. Parkfield really has produced roughly regular magnitude 6 earthquakes for over a century. The lesson is that a real rhythm and a reliable calendar are not the same thing. A fault can keep both truths at once.
Z's original number for that stretch of fault gave an average interval of about 135 years between major ruptures. That figure was drawn from 9 or 10 events across 14 centuries, all recorded at Pallet Creek, closest to Los Angeles. The last of those events was the 1857 Fort Tejon earthquake. It struck at 8:20 in the morning on January 9th, an estimated magnitude 7.9. It tore open roughly 225 miles of ground between what is now Parkfield and the town of Wrightwood. Surface offsets measured afterward at Wallace Creek in the Carrizo Plain reached 9 meters, close to 30 feet in a single motion. Streams that had flowed straight for centuries were bent sideways in an instant. Witnesses across the region described trees uprooted where they stood,
and adobe walls collapsing outward in sheets. Rivers briefly reversed course before settling back into new, crooked channels. The shaking was strong enough to be felt as far north as Marysville and as far south as the Colorado River. Both points sat hundreds of miles from the rupture. The earthquake killed one person, a soldier crushed inside a collapsing barracks at the isolated army post that gave the event its name. On the exact same side of the planet that year, a rebellion against colonial rule was erupting across India. That event would fill history books for the century that followed. The earthquake that tore open a quarter of California barely earned a footnote anywhere outside the state. Almost nobody was there to write one. Fewer than 1,000 people lived along the entire rupture line in 1857. California's total population that year sat somewhere under 400,000. The fault released nearly the same amount of energy the region will eventually face again.
The casualty count was decided entirely by who happened to be standing on the ground that morning, not by the size of the earthquake itself. Here is the part of the story that even careful viewers tend to miss. Fort Tejon and Pallet Creek sit on one stretch of the San Andreas, running from Parkfield down to the mountains above Los Angeles. The section this story is really about sits further southeast, from San Bernardino down through the Coachella Valley to the Salton Sea. It did not rupture in 1857 at all. It kept its own separate clock. C returned to that stretch later in his career, digging new trenches near the town of Indio. His first pass at the data suggested an average interval of around 200 years between major earthquakes there. Later researchers worked with more sample sites and refined radiocarbon methods. They narrowed that figure to a best estimate near 180 years, with a range from roughly 120 up to 240. The most recent large earthquake on that stretch was dated to around 1680. Run the arithmetic forward from there, and the interval since is over 3 centuries, comfortably longer than even the high end of the expected range. Researchers who work on this segment have called the open interval curiously long. It is a polite way of saying the numbers no longer add up in the fault's favor. If you set the fault's other neighbors beside it, the pattern gets harder to dismiss. The Mojave stretch near Pallet Creek runs on something like a 135-year clock and is currently 169 years past its last rupture. The Coachella Valley stretch runs on something like a 180-year clock and is currently over 330 years past its own. Two adjacent sections of the same fault, two different rhythms, both well past due at the same moment in history. That is not a coincidence anyone has been able to explain away.
It is simply what the record shows. The towns sitting on that same rupture line today are no longer empty. Coachella, Indio, and Palm Springs together hold a population in the hundreds of thousands. They sit inside a broader inland empire and Los Angeles basin population running well into the tens of millions. California's statewide earthquake early warning system, Shake Alert, now blankets the region with sensors. It is built to detect the first, less damaging waves of an earthquake and issue an alert before the more destructive shaking arrives. Residents are asked to register for the free MyShake app. Schools across the state run scheduled earthquake drills built around the same drop, cover, hold on instructions issued after every alert. In the most recent Great California Shakeout drill, more than 10 million Californians registered to practice it. Over 4 million of them live in Los Angeles and Orange counties alone. More than 5 million of the statewide total were school children and staff, drilling across hundreds of districts on the same morning. Southern California experiences roughly 10,000 earthquakes a year by USGS count. Almost none of them are ever felt. None of this infrastructure existed in 1857. All of it assumes there will be at least a few seconds of warning to use. Here is the strangest fact in the entire story, and it does not get flagged nearly often enough. The San Andreas does not run as one continuous, evenly behaving line through Southern California. Roughly 70 miles northwest of the Salton Sea, near a mountain gap called San Gorgonio Pass, the fault splits into a tangle of overlapping strands. It converges there with the separate San Jacinto Fault, inside a zone so structurally complicated that seismologists still cannot agree how it behaves. A large earthquake there remains a genuine open question.
Caltech seismologist Hiro Kanamori co-developed the moment magnitude scale used to measure large earthquakes today. For decades, he studied what happens if a rupture starting at the Salton Sea jumps through that tangled pass. If it reaches the fault's central section, the combined event could hit magnitude 8.2. That releases roughly 10 times the energy of the scenario most planning documents currently use. Nobody has recorded that pass rupturing in the instrumental era. Nobody can rule it out either. It is worth connecting this to a fault system on the opposite corner of the country's western coastline. The Cascadia subduction zone off Washington and Oregon is capable of its own catastrophic rupture. It carries its own decades-long silence, a hazard covered elsewhere on this channel. It runs on an entirely different kind of plate motion. It is governed by the identical underlying rule.
Strain that is not released keeps accumulating, regardless of how long the silence lasts. Cascadia, being a subduction event, would at least hand coastal communities a rough window of minutes before tsunami arrives. The San Gorgonio scenario offers no such courtesy. The rupture and the shaking happen in the same place at the same moment, with nothing in between. California's answer to that gap is a system built entirely around speed, not prediction. Shake Alert cannot say an earthquake is coming. It can only detect one that has already started. The system relies on a simple physical fact. The first seismic waves to reach a sensor, called P waves, travel roughly twice as fast as the slower S waves that actually shake buildings apart. The system's algorithms compare incoming data from hundreds of ground sensors. If the estimated magnitude and location clear a minimum threshold, an alert goes out within roughly 4 to 20 seconds of the earthquake's start.
In the best case, someone tens of miles from the epicenter gets several seconds of warning before strong shaking reaches them. Those seconds are not only for people. Alert partners have built automated responses around the same signal. Elevators are programmed to stop at the nearest floor and open their doors. Trains are programmed to slow before the shaking arrives. Gas valves and water systems are programmed to shut automatically at key junctions. None of these actions require a person to react in time. They only require the alert to arrive before the shaking does. The system deliberately withholds alerts below a certain magnitude to avoid flooding the public with warnings nobody would even feel. A formal review of its performance between 2019 and 2023 found it missed roughly a fifth of qualifying earthquakes outright. Most of the misses came at the edges of its sensor network. For a family living directly on the fault trace, where the rupture begins, that head start effectively does not exist. The alert has to outrun the shaking to be useful. The closer you stand to where the rupture starts, the less distance the alert has to work with. That is the system's honest central limitation. It buys time in proportion to how far away from the danger you already happen to be standing. Layer the population numbers on top of that limitation, and the exposure stacks quickly. Roughly 10 million people sit within the zone of heaviest expected shaking in the leading government planning scenario for this fault. 24 million sit within a wider radius that would still feel strong, damaging motion. That scenario, built by more than 300 scientists and engineers for the United States Geological Survey, does not stop at shaking alone. It models what happens afterward, in the hours the cameras never reach.
Roughly 1,600 fires ignite within the first day, sparked by ruptured gas lines, downed wiring, and damaged appliances across the basin. Combined, they are projected to destroy some 200 million square feet of building stock, roughly equal to 133,000 homes. Fire alone accounts for tens of billions of dollars in losses. That is on top of separate damage from the shaking and from months of disrupted water service. The same scenario estimates roughly $200 billion in total economic loss. That is more than any other single natural hazard planning document has modeled for an American metropolitan region. It exceeds the combined damage totals of most hurricanes to strike the United States mainland. And here is where the regulatory gap from earlier in this story returns, carrying its full weight. The buildings still waiting on their retrofit deadline in 2041 are not waiting in some hypothetical future.
They are waiting inside a window the fault itself has already overshot. By its own recorded history, that overshoot runs well over a century on its southern section alone. Government hazard modelers have translated all of this scattered evidence into one working figure for the entire state. The official statewide forecast, built by the same collaboration of state and federal scientists, delivers a stark number. The odds of a magnitude 6.7 quake occurring somewhere in California sit at better than 99% within the next 30 years. For the greater Los Angeles region specifically, that figure sits at roughly 60%. Numbers that large stop reading like probability and start reading like scheduling. Recent forecasting narrows the odds further for this exact fault. A magnitude 7.5 or larger earthquake striking Los Angeles County specifically sits at roughly 30% within the same 30 years.
30 years is not an abstraction borrowed from geologic time. It is the length of a standard home mortgage. It is the distance between someone's 25th birthday and their 55th. A child born in the Coachella Valley this year has a meaningfully better than coin flip chance of living through it before finishing a single career. One variable in this story genuinely did not exist during the fault's earlier ruptures, and it has nothing to do with plate motion. Southern California's fire risk after a major earthquake depends heavily on two things: how dry the landscape already is when the ground breaks, and how hard the Santa Ana winds are blowing through the canyons at the time. Extended multi-year droughts leave more dead vegetation in place for longer stretches of the year. Climate researchers have documented these droughts becoming more frequent across the region in recent decades.
That widens the calendar window in which a ruptured gas line or a downed power line can ignite something no fire crew can outrun. The 1857 earthquake struck in January during the wet season, with the landscape at its least flammable all year. A quake of similar size arriving in a dry September inherits a very different risk. With Santa Ana winds already blowing, it carries a fire risk the 19th century never had to test. The physics of the fault has not changed in 300 years. The tinder waiting on top of it increasingly has. Every generation living along this fault assumes the valley it was born into has always looked this way, flat and settled and permanent. It has not. Every quiet year the fault stays locked adds roughly 2 more inches to the debt. On its southern section alone, that debt already runs close to 20 feet. Every quiet decade adds the height of a small child. Every silent century adds the length of a city block. Palm Springs is an ordinary desert resort town sitting directly on top of a fault capable of an 8.2 rupture. Indio is an ordinary agricultural community sitting on the same trace. San Bernardino is an ordinary inland city, its downtown built across ground that tore open completely in 1857. Los Angeles is an ordinary metropolis of roughly 4 billion tons of concrete and steel. It rests on a plate sliding northwest at the speed of a fingernail growing. That plate carries the city's entire weight, whether the city notices or not. None of these places were chosen to sit above a locked fault. They simply grew where the desert happened to be flat and the water happened to be reachable. The freeway happened to be cheapest to build in a straight line. The fault was there first, patient and unremarked, for 15 million years before any of them existed. If you want more of these forgotten patterns traced out in detail, subscribing helps.
It is the easiest way to catch the next one before it disappears back into the archive. Carrie C's original number for the fault was never really a single figure. It was closer to a range, a scatter, a rhythm with real variation built into its bones. That is the same kind of variation that let Partfield's magnitude 6 clock run 11 years past its own confident prediction. The Coachella Valley section has now run past its own average interval by well over a century. It carries a measured slip deficit that satellites in orbit and mud in a desert marsh both independently confirm sits close to 20 feet. That is not a forecast. It is an account still open, collecting interest in silence. That ground currently hosts interstate highways and an aqueduct. It hosts a retrofit deadline stretching to 2041, and several million people who rarely think about any of it. The fault has already told its own story once, in 1857, to almost nobody. The only question this account has never been able to close is whether the next entry gets read by more people than the last one, or simply by more of them, standing closer with less warning than they assumed they had. The San Andreas runs the length of California, roughly 750 miles from the Mendocino coast to the Salton Sea. It has been doing this same slow, patient work for at least 15 million years. Humans arrived late to a ledger that was already centuries deep. The fault does not need anyone to read it in order to keep writing. It only needs the friction to fail once more, on whichever section runs out of patience first.